morning, everyone. Myself, Dr. Rajesh Prasad. I'm working as professor in Akgec Engineering College, Ghaziabad. So today I'm going to discuss the recursion tree method for solving the recurrences. So why it is needed? But important thing is that limitation of the master method. Master method used to fail if in certain conditions, like say. So if we think about master method, so case one is like if you see the recurrence Tn is Atn by B plus Fn. Okay, so if this is the recurrence, so in the case number one, and if you see if Fn is big O of n to the power log A base B minus epsilon, okay, and where epsilon is a positive thing, so this Tn should be theta n to the power log A base B. This is the case one. Case 2, if Fn is like theta of n to the power log A base B, then Tn will be this. This is the solution. And case 3 is if Fn is omega of n to the power log A base B plus epsilon, then regularity condition is also satisfied, Afn by B less than or equal to Cfn, then Tn is actually theta of Fn. So if we think about this type of recurrences, like say Tn is 2 Tn by 2 plus, let's say, n log n. See here. So in this situation, none of the method is working. Case 1, case 2, case 3. 3 of the method will fail, because if you look at here, Fn is n log n, okay, and then it is not possible to have this equal to like theta n to the power log A is 2, B is 2. So this is actually theta n. So this is not equal to this. So case 1 failed. Okay. So if you go to the case number 2, case 2 is also not equal to this. This is not equal to this. Case 3 seems to be applicable, like n log n greater than this, right? But actually whenever you are computing this regularity condition, it will fail. Okay. So that means all the case 3, 1, 2, 3 failed in such type of recurrences. Actually, the big problem is that, together with this condition, we need to check whether this guy is polynomially smaller than this or not. See this, like if you are talking about this guy is less than or equal to this one, like here, first one, if Fn is less than or equal to like almost less than or equal to n to the power log A base B minus epsilon. See, almost literally this. In order that this is less than or equal to this also, so Fn should be polynomially smaller than this also. What is polynomially smaller? Means that Fn divided by n to the power log A base B less than n to the power epsilon, right? So if this is the situation, then this guy is less than polynomially smaller than this. On the other hand, also in this situation of the case 3, Fn should not be only greater than this value, Fn should be greater than or equal to n to the power log A base B, but Fn should be polynomially greater than this also. That means Fn by n to the power log A base B greater than n to the power epsilon. In this situation, if you look at here, this guy Fn is n log n base 2 is not polynomially greater than this value. You see here, n to the power log A is 2 and B is 2. So this means that this is n log n divide by n. So it will cancel it and it will become log n base 2, and this is not greater than n to the power epsilon. So that means this master method will fail if we are getting this type of recurrences or a situation when this is not polynomially larger than this and this is not polynomially smaller than this. So in this type of situation, we are actually considering the recursion tree method. It is a very general method. So what are the steps to solve the recursion tree? You need to draw the recursion tree first and compute the cost at each level of the tree, right? After computing, you just calculate that which one is higher, like see. So I'm dividing the recursion tree questions into 4 categories. Category number 1, especially like this is the category where cost at each level is the same, right? So like here Tn is to Tn by 2 plus n. So make this as n, make this as a root node, okay? N is the root node and this guy will be the leaf. So we know that this can be written as Tn by b 2 plus Tn by 2 plus n. So what is actually happening? This is n and then this will be Tn by 2, Tn by 2. Actually this is the situation, right? So if you go Tn by 2 again, so if you see Tn by 2, so this is 2 Tn by 4 plus n by 2. So again, if we expand it, this will be here and Tn by 2 will be here, n by 2, and then this is Tn by 4, okay, and this is Tn by 4. Similarly, this Tn by 2 is n by 2, Tn by 4 and Tn by 4. Actually, this is the situation, okay. So look at here. So if we what we are actually doing, if you sum the cost, like see, this will keep reducing and it will go up to, let's say, T1. Ultimately it will finish, it will go up to T1. Clear? So what is actually final answer? This is T1. So what we are going to do, we are going to add the cost at each node. See, this is n and add them together. So this will become n again. Cost at each level will be the same. Same thing here. After expansion, it will be n also. Okay. So cost at each level of the tree is going to be 1. So in this recursion tree method, we need to consider only 2 things. First one, cost at each level, sum them. So actually, if you look at this tree completely, okay, this is non-leaf node, okay, this is non-leaf node and this is leaf node, So total cost will be leaf node, okay, leaf node plus non-leaf node. Yes. This is actually total cost. So first question is arising actually when we are reaching T1. This is question number 1. Okay. So when we are reaching T1, how to calculate it? Look at this. How this is reducing? This is reducing as n by 2. So ultimately T1 is reached only, okay, when n by 2 to the power I equal to 1. That is it. Simple. Because at ith level, we are assuming that this is going to be 1. So by this method, I will be log n base 2. This is the first finding, right? So check how it is reducing. If it is reducing as n by 2, so this is n by 2 the power I is 1. So from here you get I equal to log n base 2. Number 1. Number 2, calculate how many children at each levels we have. So we have at each level number of children is equal to 2 to the power I, right? That means to the power I from here you compute it log n base 2. So this is actually n to the power log 2. So this become n. This is number 2. So we got this, okay. So how to compute it? Let's say, so you see here, this is the non-leaf, add them together, non-leaf plus leaf node, okay. So non-leaf, how many they are here? So if you add them together, so this is the problem is like this is the leaf node. Okay, so this is the non-leaf, this is the non-leaf node, and this is the leaf node. They are T1. So this is the leaf node. Okay, this is the leaf node, and this is non-leaf node. This is non-leaf node. Okay, yes. So this is non-leaf, this is leaf node. So if you add them together, so n is n added how many times? 0 to I minus 1. They are the non-leaf node. So 0 to I minus 1 means log n base 2 minus 1. So this will become log n base 2. Log n base 2 times. Okay. Yes. So this actually is n into log n base 2, and this is cost of the leaf node. So if you look at here, so this is the solution, this is the Tn, and if you add them together, you will see that this is equal to big O of theta of n log n base 2. So this is the first example where cost at each level remain the same. Second category of the example is that when cost at each level is not actually the same. Look at here. For example, if we look at Tn is 3Tn by 4 plus Cn square, methodology remain the same. Okay, so this is Tn, number 1. If you look at here, this is Cn square. Okay, and then this is Tn by 4, 3 part, it is divided into 3 part. Okay. Similarly, if you just expand Tn by 4 again, so if you expand Tn by 4 again, so this is Tn by 16 plus Cn is n by 4, n square by 16. Okay, n is replaced by n by 4. So this is actually this value. Okay, so now Cn square by 16, Cn square by 16, Cn square by 16, this is categorized into 3. So by doing this, if we will see this like cost at the root level is Cn square, cost at this is 3 by 16 Cn square, cost at this is 3 by 16 square Cn square. Keep adding them, and again question is that so cost, total cost will be here. You know, this is non-leaf node. Okay, this is non-leaf node, and this is leaf node. Okay, this is leaf node, and this is non-leaf node. Clear? Okay, so in the recursion tree, again first one, when we are reaching T1, that is the important objective, right? When we are reaching T1 is important. So question is that how problem is reducing? Problem is reducing as n by 4 to the power I. Okay, so this become 1. It means that I will be log n base 4. This is number 1. That means it is reducing when I is log n 4. This is the value. Okay. So how many parts each like children they have? So this is dividing into 3 to the power I. This is number 2. So 3 to the power I is log n base 4. This will come over here. So n this is actually yes. So the number of children are n to the power log 3 base 4. So if you start adding the non-leaf node and the leaf node, so this is the solution of the leaf node. They are T1, and 3 to the power I is the 1. So this is the solution of the leaf node. Okay, and you know that how many they are? They are 0 to I minus 1. So they are 0 to I minus 1 is log n base 4 minus 1. So number of non-leaf nodes are log n base 4. They are the one. So this is how it is added. 0 to log n 3 by 4. This is geometric progression 3 by 16. So this is 3 by 16 to the power I Cn square plus this. Actually, we are interested in finding out the upper bound. So in order to get upper bound, we are just taking it to the infinity. So this I will range from 0 to infinity. So 3 by 16. And of course, this is a geometric progression, and we know that some of the geometric progression is Tn is A divided by 1 minus r if common ratio is less than 1. Otherwise, a by r minus 1 if common ratio is greater than 1. So here common ratio is like this is the series 0. This is the series 3 by 16 to the power 0, 1, then 3 by 16, then 3 by 16 square up to and so on. So first term is 1 and common ratio 1 minus r, common ratio is 3 by 16. So if you just compute it, it will be 16 by 13 cn square. So, so if we just approximate it, so this is going to be big O of n square. This is the second category of the question. So let's understand the category 3 of the questions, right? So this is important when there is like uneven partition. Look at here. It is not like similar to this Tn is A Tn by B. This is not like that recurrence. This is important category of the question. So this is uneven partition. Okay, especially very useful when we are solving the sorting quick sort algorithm. So this is Tn by 4 plus this plus this. So of course you look at here, so same technique if you are applying, so Tn will be here, then this in place of Tn this will be n, and Tn by 5 left hand side and T4n by 5 right hand side. Again this can be expanded, this can be expanded. Look at here, so how it is expanded. So if you look at here n level 0 and then this Tn by 5. If you just start expanding, Tn by 5 is n by 25 plus Tn by 5. So 4n by 25 plus n by 5. Okay. So this is like going to become n by 5. Okay. And then this is the left child and this is right child. This is left child, this is right child. Similarly, if you start expanding T4n by 5, so this is the situation. Okay. So after one thing we might have noticed that cost at the each level remain the same. So this cost at root is n and cost at this is also n. Similarly, you will see that cost at each. So in this type of questions, we are always interested in the longest path, right? Yes. We are always interested in the longest path because this may finish first and this may finish later on. So the last one which is finishing is the longest one, right? So this will be finishing in the longest one. So overall time will be actually approximated to the longest path. Okay. So how this longest path, what is the longest path? 4 by 5. 4 by 5 to the power I. Okay. So this is the one which is finishing in the last. By doing this, I will be log 5 by 4 and n. This is the first point. So total number of node maximum can be this. So total number of node can be this. Okay. And we know that problem is always dividing into 2 to the power I. We are interested in maximum. So this to the power I can take from here into T1. So this is the actually leaf cost. This is the leaf cost. Okay. So total cost, as it was discussed, that this is the non-leaf cost plus this is the leaf cost. Okay. And how many they are? They are maximum is log n base 5 by 4. This is the one. So if you just add them together, so this is the time. So okay, so this is Tn is theta n log n. This can be approximated to this. Okay. So last category of the recurrence relation which cannot be solved by any of the method, which can be only solved by this method, is Tn minus 1 plus n. This is actually like this can also be written as Tn is Tn minus a plus n. This can be a, b, c, anything. So if you draw the recursion tree in the same method, this is n and then again you see here n, then Tn minus 1, okay. And again if you start expanding, Tn minus 1 will be n minus 1, then Tn minus 2, okay. Then n minus 1, Tn minus 2 will be n minus 2, and then Tn minus 2. Keep continuing like this, okay. So if you start adding them, n, then n minus 1, then n minus 2, ultimately you know it will become 1. So at what time it will be 1? Whenever n minus I equal to 1. It is reducing as this, I will be n minus 1. So this is the 1 actually, okay. So if you just add n plus n minus 1, keep adding, and then up to it will take up to 2, and then big O of n. This is actually an arithmetic progression sum. If you add them together, they are like 2 to n minus 1 term. So we know the formula of Sn. Sn is n by 2, nth term, 2a plus n minus 1 into common difference. Here we have n minus 1 term, so if you just add them together, so n minus 1 by 2, okay, and 2 first term is n plus n minus 2, n is replaced by n minus 1, common difference will be minus 1. This is the solution, okay. So you will get big O of n square as the solution, okay. So this is very important method for solving the recurrence. You can generalize this to any other method, like see here, Tn is Tn minus 2 plus let's say n. So in general, if something is like Tn is Tn minus k plus n, so its solution is always, whatever it is written is just like is square, right? So if question is like Tn is Tn minus k, okay, and plus let's say n square, its time will be Tn is theta of whatever is value, it is increased by 1. So this can be approximated, right? So for reference purpose, you can see this like Corman and Knuth and Donald. Thank you for watching.